now that we have seen all the basic formulations, I will give some examples to help you to give you some concrete uh, formulations for the general problems that we outlined in the previous lecture. All right. So the first example we consider is perhaps the most popular one in binary hypothesis testing. In this case, our unknown x can take two values, either s or minus s. And what we observe is y. So I'm calling this thing x because this is the unknown and I observe y, and from y I would like to infer something about x. So this goes back to the basic question that we started with, namely how much information that does y reveal about x. All right. So there are two hypotheses we have. There are two possible hypotheses. First is that y is distributed as a Gaussian random variable. So this is a Gaussian random variable or a standard or a normal random variable. Okay. So this is a Gaussian random variable with mean minus s and variance sigma squared. Okay, that's my notation. So this is the mean and this is the variance of my Gaussian random variable. So under h0, this mean is s, and under h1 this mean is under h0 it is minus s, and under h1 it is s, and the variance is same under both the hypotheses, sigma square. So as we saw earlier, if we look at uniform prior and look at a Bayesian formulation where first x equal to minus s or s is selected with probability half each, and then you observe y from this distribution, in that formulation the minimum probability of error that you can have is half into 1 minus total variation distance, this quantity here. And this total variation distance is the total variation distance between the distribution y under minus s and distribution y under s. These are these two distributions. Okay, so what is the total variation distance? It is the probability. If you recall, the total variation distance d minus w minus s ws. So I'll write it here. D pq has various expressions. The ones I'm using here is it's p of a star minus q of a star, where a star is the set of those values for which px exceeds qx. Okay, that's the definition we had seen for the discrete case. For the continuous case, this is a set of those values for which the density of p, f is the density of p, is greater than the density of q, which is g, let's say. Okay. So for this particular example, denoting by w, so this is some slight abuse of notation. W minus s here denotes a density of y under hypothesis minus s and density of y under s. So this is p of a star minus q of a star. Pictorially, you can pictorially see this set. This green curve represents ws. So this is the Gaussian distribution with mean s. This blue curve represents w minus s, Gaussian distribution with mean minus s. And this set where w minus s exceeds ws is the left side of 0. You can see that in this part, w minus s exceeds ws. And this set is the right side of 0. Okay, so we can exactly identify these sets. So this set here is the equivalent to y, that y is less than or equal to 0, and this set here is equivalent to y such that y is greater than 0. Where you put 0 doesn't matter. Okay, it has 0 probability because it's a continuous random variable. Okay, so then what is the probability of a star under w minus s? This probability is given by, you can check this. So we can write this y, this is the probability that random variable y is less than equal to 0 or less than 0. And this random variable y is z plus z minus s, because where z is a standard Gaussian random, z is a Gaussian random variable with mean 0 and variance sigma squared. So y was Gaussian random variable with mean under w minus s, y is a Gaussian random variable with mean minus s and variance sigma square. So I took out that minus s, so I get this z. So this first part of the probability is just 1 minus probability that z, a Gaussian random variable with mean 0 and variance sigma square, exceeds s. Okay, so this probability here is typically denoted by this Q function. This Q of t is simply the right tail of a Gaussian distribution. So Q of t, if this is the Gaussian density, is this area in the right part of t. Okay, that's what Q of t is. And therefore you can express this probability as Q of S by sigma. So you divide by sigma because this is the, in this notation, Q function corresponds to standard normal random variable, but we are looking at a Gaussian random variable or normal random variable with variance sigma square. So we divide by sigma and then it's the same thing. So S by sigma, Q of S by sigma. This is how the Q function is defined. Okay. Similarly, Ws of A star is equal to Q of S by sigma as well. So this is 1 minus Q of S by sigma. This is Q of S by sigma. You can verify this. Right. Therefore, this total variation distance between Gaussian with mean minus S and mean S is 1 minus 2 times Q of S by sigma. Therefore, the probability of error is 1 minus total variation distance by 2, which is Q of S by sigma. Okay, that's the probability of error. This expression is sort of very popular. It comes up in many places. For instance, communication engineers may have seen it in analysis of probability of error for BPSK scheme in presence of Gaussian noise. Okay, so this PE star uniform is Q of S by sigma, and there's a very nice approximation for the Q function, which is also easy to remember. It just looks like the Gaussian density itself. So Q of S by sigma is approximately equal to, you can find a precise statement here, but I'm just giving a rough statement. It's approximately equal to e to the power minus S square by sigma square. So this approximation is useful to remember. Q of t, the right tail of a Gaussian random variable, this is called the right tail, is approximately equal to e to the power minus t square by 2. So it goes to 0 very fast, as fast as the density of Gaussian. Okay, so this one is just this one. So this is the probability of error. This is the best probability of error for uniform prior that you can attain for the first example. Okay, so let's look at another example now, the second example. Yeah, now it's very similar to the first example, but now x and y are vectors, d-dimensional vectors. And we assume that under both, so x and y are d-dimensional vector and y is rd as before, and x is not a single value, but x can be any vector here. So this is an estimation problem. And given x, the distribution of y is this normal distribution with mean x, remember this is the vector, and variance sigma square I. So again, y is a Gaussian with mean x and variance sigma square I. Our goal is to estimate x by looking at y. Okay, so you can consider this very simple estimator. This is like a sort of a naive estimator. It just declares y. When it sees y, it just declares y as an estimate for x. So you can check that for this estimate, the loss, the expected loss of this estimator g given px for any px is d sigma square. Remember, so by the way, this loss we are going with is the mean square error loss. We defined this in the previous lecture. Mean square error loss expected. So maybe I'll revise it here. So what is the loss that we are computing? It's the expected value of, so I observe y and I use my y to estimate x by using this function g. So my estimate for x is just g of y. Okay, and we do this error, and this expectation is over the distribution of x, and then y given x is fixed to this channel. So then you can check that this guy, no matter what px is exactly equal to, for our choice of so for our choice, which is gy equals to y, this is exactly equal to d sigma square. Okay, so we saw one estimation problem, namely that of mean estimation, by looking at a noisy version of it, and proposed a very simple estimator and saw that what error performance we get. Okay, so this is another toy problem, just to give you an example of an estimation problem. Let me now come to a very interesting problem, one of my favorite example for introducing hypothesis testing. Okay. This problem is that of testing the bias of a coin. So here is a very simple version of the problem. How many coin tosses are needed to test if a coin is head heavy or tail heavy? So what is a head heavy coin? Head heavy coin is the one which shows heads with more probability than tails. Tail heavy coin is the one which shows tails with more probability than heads. Okay, and an unbiased coin is the one which shows both heads and tails with equal probability. So let me try to articulate this problem. So here it's a very simple problem to state. What I'm saying here is that you have a coin and you want to figure out if it's head heavy or tail heavy. How many times do you need to toss the coin to answer this question with good reliability? So let's formulate this problem in our framework, the hypothesis testing framework that we have introduced, the general formulation that we have introduced. So the alphabet X, the unknown X, it corresponds to now the probability of heads or tails. So you can think of this as probability of heads. So either it is half minus epsilon or it is half plus epsilon. Epsilon is some small parameter, let's say 0.01. So it's either 0.5 minus 0.01 or 0.5 plus 0.01, and that's what you want to figure out. If the coin has bias half minus epsilon or half plus epsilon. The question is how many times you need to toss the coin. Okay, what is the observation? Observation is n coin tosses. You toss the coin n times, let's say. So the observation is 0, 1 to the power n. So under hypothesis H0, you get y1 to yn, which are IID copies of a Bernoulli random variable with a probability of 1 being half minus epsilon. This is my P. Under H1, you get y1 to yn, which are IID Bernoulli half plus epsilon. Okay, this is H1. This is my Q. I'm denoting it by Q, this IID distribution. So this I'm calling P, this Bernoulli, and this Bernoulli I'm calling Q. So under H1, our observations are from this Pn. This notation is something I'll use again and again. P superscript n denotes this product distribution. It denotes the IID distribution with common distribution P. Similarly, Q superscript n is this Q cross Q cross Q. Okay, Qn. So this is the n-fold product distribution on y1 to yn. Okay. So we already have a formula for P star. Okay. We saw that this P star under uniform prior, the uniform prior version is the one we are going with, is half into 1 minus total variation distance between Pn and Qn. Okay. So suppose we will be happy with a small probability of error which is smaller than 1 by 2000. That's some bar that we have kept. Suppose we'll be happy with such a reliability. Then how many coin tosses we need? So this question basically tantamounts to understanding how the distance between Pn and Qn grows with n. As I said, you can understand a hypothesis testing problem based on this distance. Distributions which are at a constant distance apart are distinguishable with constant probability. So to make this smaller than 1 by 2000, you want this distance to grow above some constant. What is that constant? We must have that this distance exceeds 999 by 1000. Pn Qn exceeds 999 by 1000. Okay. So as n grows to infinity, this Pn and Qn, this distance will tend to 1. Actually, you can convince yourself about it. So if you have IID repetitions, the distance between Pn and Qn, the independent copy, will grow, and it will grow to 1 actually. Okay, this is something you can easily convince yourself. But at least heuristically, it's just heuristic to remember that as you have more and more tosses, this distance between the distribution Pn and Qn, the IID distributions, grows to 1. So what we are asking now is what is the least number of coins, such coin flips n, that is required for this distance to cross this quantity. So this distance starts somewhere, and then we want it to cross this quantity. By the way, where does this distance start? Can we quickly think of that? So here are the distributions P and Q. What is the total variation distance between them? So here dpq, you can check, is exactly equal to half minus epsilon minus half plus epsilon, mod of that. So dpq in this case is 2 epsilon. That's where we start from a single coin toss. And now as you toss the coin multiple times, this distance grows, and we want this distance to cross 999 by 1000. What is the least number of tosses for that? So here is one way to find this estimate. This property is very useful. It's called we can call it the subadditivity of total variation distance. It says that if you have product distributions then the total variation distance between Pn and Qn is at most sum of total variation distance of each component. So P1, this is the product distribution, this is the product distribution. In our application, they're all identical, but this property holds even when they're not identical. They can be potentially different. So the total variation distance between P and Qn is at most sum of total variation distance of each coordinate. Okay, this is a result. Actually, the proof is not so difficult. Proof is roughly triangular inequality, and we will show this, and it suffices to show this for n equal to 2. Okay, I left this question here. Why does it suffice to show it for n equal to 2? Well, you can take a pause and think about it. Okay, now that you've thought about it, I'll quickly explain. So once you show this property for n equal to 2, then you can apply this. So you can apply this particular property for n equal to 2 with P1 and Q1 as this one, and with the remaining P2 to n and Q2 to n in place of P2 and Q2. Okay, so that's how you can apply the property for n equal to 2. And then you can recursively repeat the argument. You will get the argument for any n. Okay, so we just need to show it for n equal to 2. How do we show it for n equal to 2? It's just triangular inequality. So we have look at this quantity. It looks like this when we expand. I'm just showing it for a discrete distribution. So it looks like this. I'll add and subtract this P1 of y1, Q2 of y2. This is a fictitious distribution. Doesn't exist in our analysis, but we made up something which has P1 for the first coordinate and Q2 for the second coordinate. And I add and subtract this quantity. Then I can use triangular inequality to get these two bounds. Okay, so if you look at this first part here, we can take out P1 y1 common here, and it will add up, and it will become just d of P2 Q2. Okay, and similarly the second part will just become d of P1 Q1. So this thing is exactly equal to this. Therefore, what we have shown is d P1 cross P2, Q1 cross Q2 is less than equal to d P2 Q2 and d P1 Q1. So I'm not sure how many of you have seen this property before. Perhaps since you are all new to information theory, the definition of total variation distance itself is new to you and you haven't seen it. But interestingly, this thing comes up quite a bit in cryptography. This is sometimes called the hybrid argument in cryptography, and it's used quite heavily in this is a component of the hybrid argument. Hybrid argument is a slightly complicated creature, but it's used for formal security analysis quite a bit. But at the heart of it, it's a very simple triangular inequality. And this argument, specifically this argument, is what is called hybrid argument. Okay. And just easy to remember, okay? So total variation distance is sub-additive for product distributions. All right. So now we have some property of how total variation distance grows. So this guy grows like n, dp and qn grows like n. So this can at most be, by applying this property, this guy is at most n times dpq. Remember dpq was 2 epsilon, so this is at most 2n epsilon. So when we use this bound and apply it here, I missed a factor here. This should be 2 epsilon. But anyway, we don't care about constant so much in this discussion. Okay, so for probability of error to become less than 1 by 2000, we want n to exceed this, where dpq is 2 epsilon, and therefore we need approximately 1 by epsilon coin tosses to distinguish the two coins. Okay, that's what this bound suggests. So how good is it? Actually, this bound is not very good. We'll see later that this bound is too weak, and we'll need many more coin tosses. In fact, roughly we'll need 1 by epsilon square coin tosses. Okay, not 1 by epsilon as suggested by this bound. We need 1 by epsilon square. So just to appreciate our difference between 1 by epsilon and 1 by epsilon square. So remember that our nominal choice of epsilon was 0.01. So we were looking if the coin has bias 0.51 or 0.49. Okay, and for that 1 by epsilon says that you need roughly 100 coin tosses, whereas 1 by epsilon square says no, you need actually 10,000 coin tosses, which is much bigger than 100. Okay, so this is an order-wise difference. So this bound is really weak, and the reason this bound is weak is because we were a bit loose in our estimate of growth rate of dp and qn. We will see that dp and qn actually doesn't grow like n; it grows like square root n. So it's not less than equal to n; it's less than equal to square root n. Okay? So that's this improvement we'll come back to later. So, so I hope I have conveyed some concrete version of hypothesis testing problems to you, and I've also, through this examples, tried to bring out the information theoretic flavor of this problem. For instance, in this last coin toss problem, what we tried to understand is how much information is revealed by each coin toss. Now, this is a loose statement. What we have understood is that probability of error under uniform prior, the Bayesian probability of error under uniform prior, is directly related to the total variation distance for binary hypothesis testing. And if we if we are looking for a particular probability of error, then we can directly connect the total variation distance to the information, and then we can ask how this information grows as we have more and more coin tosses. And what we did here was to get in some estimate of how this information grows. It looked like we were saying that information grows like at the rate 1 epsilon. So when you have n coin tosses, the information you would have had is at most n epsilon. This resulted in a minimum number of coin tosses bound of 1 by epsilon. But actually this is not right. We can derive a much better bound, as we'll see later. All right. So in the next class, I'll present a slightly different formulation for the hypothesis testing problem. As till now, we have mainly looked at the Bayesian formulation. It's called the Neyman-Pearson formulation. It is also of interest to us. And as we saw that the Bayesian formulation brought out total variation distance as the handle over its probability of error, this Neyman-Pearson formulation will bring out a slightly different notion of distance between P and Q, which is more popular in information theory. All right. So see you in the next lecture.